Hi. In this video for computer architecture, we're going to demonstrate running the little 8080 program we wrote in the last video on an actual CPU, an actual computer that has an 8080 CPU. This is an MITS Altair 8800, one of the first commercial microcomputers introduced in the mid-70s, and it has an 8080 CPU. The front panel here is very similar to the front panel in the PDP-8. We've got a row of LEDs for the data bus. The 8080 is an 8-bit CPU, and consequently can store a number between 0 and 2 to the 8th minus 1, 0 and 255. If you want to store bigger things, like a floating point number, which requires a minimum of 32 bits, you've got to store it in chunks and write software to manipulate the floating point numbers. Now, given that the address bus is only 16 bits, that is, the full memory of the computer is about 64K of DRAM, those subroutines take up a fair amount of memory, and in fact, just even getting a full-featured operating system is sort of a chore. I'll turn the machine on. We've also got a row of switches to enter data or addresses, a row of control switches, and a row of lights that tell us the status of the CPU. The switches we've got on the control row, there's a power switch, which I turned on, a stop-run switch, which does the obvious thing, a single-step switch, which causes the processor to execute a single instruction, an examine next switch, which causes you to look at the contents of the address that's specified in the switches. Deposit and deposit next cause you to change the contents of the address that you're presently examining based on the values of the lower 8 switches. Reset will reset the CPU, so let's go ahead and do that since we just turned it on. Protect and unprotect. If the memory is protected, which it is because of this light here, you can't change what's in the memory, so let's unprotect it. The light goes out, we'll be able to make changes. And these two switches labeled AUX are for expansion. You can use them how you like in your software. We're not going to use them at all. So we want to write our program at address hex 100. So that's a 1 followed by 8 zeros in binary, and I've toggled that in here, or not quite. There we go. 1 0 0 0 0 0 0 0 0. So that's hex 100. We'll examine what's at that address by flipping the examine switch up, and we see that we are at address 100, and there's some data in there, which is just garbage. But let's start putting in our program. First instruction in the program is move immediate into register A, the constant 23. So we'll first of all code the opcode 00111. That specifies we're moving into register A. 11 just part of the opcode, and then 0. So I'll flip up deposit to put that value into address hex 100. So that's good. Then the constant we're storing in register A is a 23, so that looks like 0010, 0010, that's a 2, 0011 is a 3. So we'll deposit that into address 101. Oops, I hit deposit, not deposit next, which messed up what was in address hex 100. So let me go back to address hex 100. And put the right thing in there again. I mean, I'm not sorry that happened, other than the extra time it takes me, but you get to see sort of the tediousness of this process. So let's see. Address hex 100, deposit 00111110. Okay, that's what we want there. Then we want the 23, that's 23. We'll click deposit next, put that in address hex 101. Okay, that's 23, that's what we want there. Next instruction is to move immediate into register B, the constant hex 44. Move immediate into register B, looks like that, 00000110. Deposit next puts that into address hex 102, and the value we want to deposit is 44, 4, 40. Okay, that puts the 44 into hex 103. Into address hex 104 is our add B, which is a 1 followed by 7 zeros. So we'll put that into address 104. That's just a 1 instruction, or 1 byte instruction. Then we have 2 3-byte instructions. We store the accumulator at address hex 300. That looks like 00, 11, 0010. That's the opcode for store accumulator. So we put it at address hex 105. Then we want 300 in Little Endian format, so the low order bytes of that come first. That's all zeros. And then the 3 comes after that. 6 zeros followed by 2 ones. Okay. And then we're going to jump to address 100. So we'll put the jump opcode in address 108, and then the high order bits of the low order bits of the jump address are all zeros to address 109, and the high order bits of the address into hex 10A. And that should be our whole program. Let's go back then to address hex 100 and check it out. Make sure we've got the right thing. Okay, that's the opcode for the move immediate, the data for the move immediate, which is hex 23, the opcode for the move immediate to B, the data for the move immediate to B, which is hex 44, the opcode for add B, of course the accumulator is the implied other operand there, that's right, the opcode for store the accumulator, low order address bits of the address to store, high order address bits of the address to store, jump, low order bits of the jump target address, high order jump target address bits. So that's going to address 100. So like we said, this program's just going to loop and loop and loop till we stop it. So what I'm going to do now is go back to address 100, first address of our program, and I'm going to toggle from stop to run, and then we're just going to let it go for a little bit. And you'll see the lights sort of dimly flickering while it's in run mode. There we go. It's running. If everything's right, it's written into address 300 thousands of times, the value 67. We'll stop. And let's look at address hex 300. And what we find there is exactly what we wanted. 23 plus 44 as hex values gives you 67. There's our 6. There's our 7. It did what we wanted. Now, obviously, this is no way to really program a computer. I do have a relative who programmed bank computers in the 70s who'd say that there would be times when they would toggle in binary a patch to a running program during the day when the bank was open. I just don't know that I ever would have had the courage to do that kind of programming jobs. For the most part, the front panel was in reality just used for testing and debugging. But I think it accomplishes the goal of letting you see how the hardware works without any intervening layers of software whatsoever. No software is being processed here. The bits present in a given memory location cause the circuitry to execute certain functions. And that's the way the machine runs. You'll see that in more detail as we go through it in lab, but I wanted you to see, at least on a couple of real machines, what it looks like running a machine language program in binary at its lowest level. And we'll see you in the next video.